So, dark matter. So, first of all, I think it would be nice if it's more or less interactive. So let me actually start by asking you a question. What is the minimal mass of dark matter particles? So what is the lowest mass that you can think is reasonable for a dark matter particle? I'm taking shout or whatever. So what is the lowest possible mass that is allowed with reasonable observations? And I'm not looking for a very precise number. I'm looking for some wild orders of magnitude. Any suggestions? Yeah? Okay, very good. Any suggestions why this is the case? Yeah. Okay, very good. But let me ask, who already knows about this lower limit? Because otherwise I would maybe explain it to begin with. So who knows about this 10 to the minus 20 limit, or who thinks that, or has heard that dark matter particles should be rather like a kilo electron volt? Because there's a world of difference between 10 to the minus 20 and... So who has heard the KeV limit? Okay. And who has heard about the 10 to the minus 20 and not just 1 minute ago? Okay, slightly orthogonal, but non-complete set. Okay, then let me kind of quickly recap the argument that was already made, because this is something, by now it's getting better, but this is something that has been kind of heard of in the past. But if you had asked 10 years, or if I had asked 10 years ago, I think the vote would have been much clearer in one direction than the other. So let me nevertheless kind of briefly sketch. There is a myth that the mass of dark matter particles has to be of the order of keV or so. But I hasten to stress it's a myth. And how does this come about? It's basically two reasons, and one you have already heard. The most common reason is that people assume thermal production. And why is that? And I'm just giving you the super rough outline of how it goes, and I'm not going to be quantitative. But if you have thermal production, this is something I think you heard earlier this week by Thorsten Brinkmann. You have a production temperature which is of the order of the mass of the dark matter particle divided by 30. The precise number doesn't matter too much. Of course, if you want to do something super precise, but the production temperature, if you have a thermal production mechanism, is typically linked to the mass of the particle. So that sets not just the temperature, of course. As you follow the dynamics of the early universe, this already sets you the time when something is happening. And what this tells you is that the velocity of the dark matter particles at T production is of the order, well, you can easily guess that from here, say Fu times 0.1. So it's non-relativistic-ish. It's a little bit non-relativistic, but not super non-relativistic. And of course, this is way too fast for structure formation. Okay? But of course, this is also typically way, way before structure formation. So now, the velocity of dark matter at some later temperature, or some smaller temperature, so if you wish, this is smaller than T production, well, it scales like the scale factor. So it's V dark matter at T production times A production divided by A, well, from T of T, if you wish. So later in the universe, your scale factor is bigger, your velocity is smaller. Velocity simply goes like 1 over the scale factor. But this, of course, is also and that is the ratio between the temperature at T and at production. And this is essentially T of T and related to the mass of the particle. You can insert, if you wish, a factor of 30 here, but don't worry about it. So this is a factor of 30, this is this factor here. So the important bit is, and this is what you can see here, if you go to a given temperature, an interesting temperature is, for example, when you have matter radiation equality. At that point, you have a fixed temperature. And now, if your mass is bigger, well, you have more suppression of your velocity. So at the time of interest, typically something like matter radiation equality, your velocity goes down with the mass of such a thermally produced particle. So that's why heavy particles are preferred. You can also say there's simply more time or more expansion happening from the time of production to matter radiation equality or the time of structure formation. So that's why heavier particles are, in this context, slower. So that means and then you can simply ask, how slow do they have to be for structure formation to be viable? By the way, everybody is clear why we need slow particles for structure formation? Yeah, okay, very good. Because fast particles simply do not bind. So that's thermal production. So it's arguing simply velocity goes down with the mass at the time of interest. There is the other option. This is already more restrictive, fermionic. If it's fermionic, again, not going into details, but you have Fermi pressure and velocity, and those go, both of them go like the mass of the dark matter particle to some negative power. So the pressure goes up when you reduce the mass. The velocity, the Fermi velocity, goes up when you reduce the mass, and the reason is, of course, if you keep the density fixed, you need more particles. More particles means you need to squeeze more fermions into the same volume, means you need to populate higher and higher states, in particular higher and higher velocity states. That's why you go up with the power of the mass. And those two things are the prerequisites for this myth that dark matter has to be heavy. However, as all good no-go theorems, no-go theorems usually just tell you what you need to do in order to avoid them. You can avoid the conclusion by, well, who needs fermions? You use bosons. And, well, you use a non-thermal production mechanism. And this is exactly Axions and ALPs. And that's what we are going to look at. So in that sense, we are automatically fulfilling these two conditions. Okay. Maybe next question. How much have you heard about axions already? Just a little? Okay, very brief sketch. Because axions are truly the prototype of this type of dark matter, but it's by far not limited. So people have kind of good motivation, but also, well, you could say simple phenomenological interest in looking at broader generalizations. So let's have a look at axions in a nutshell. Axions actually start from QCD. Then I'll leave a little bit of space. Psi plus, let me write it like this, psi bar m psi. This is a very simplified version of QCD. That's probably what you have all seen in Lagrangians of QCDs. This is the gluon field strength, so the kinetic terms and the self-interaction terms of QCD. This are, for example, here now just representatives of the quark kinetic terms with the covariant derivative here. The covariant derivative, of course, containing the gluons, and therefore providing also the interactions of quarks and gluons. And, of course, the mass terms for the quarks. And this is what you most of the time see. But you could also have minus 1/4 theta g mu nu tilde. So this being epsilon mu nu rho sigma g rho sigma. So this is the dual field strength for the gluons. The dual field strength is something you may know already from electrodynamics. And after all, gluons are not much different from electrodynamics in many fundamental ways. So let's kind of sketchily write that in terms of electric and magnetic fields. So the field strength square term is something like E squared minus B squared, whereas that is something like E dot B. And two crucial things about that. Basically, the dual field strength essentially swaps the role of E and B. That's why instead of E squared, one of the E's is swapped into a B, you get E dot B. One of the B's is swapped into an E, you get E dot B. Okay? That's what the dual makes, and that's what motivates this kind of structure. But more importantly, if you look at what happens under CP transformations. This is CP even, and I could also make it clearer, it's also T even, and this is CP odd. And of course, it's also T odd. So these terms are odd under CP or odd under T. And this is actually, that's why I brought up T, so time reversal. This is actually much easier to see. Because what happens to E when you change the direction of time? Nothing, because it's a static configuration. You can have a charge here, that gives you an electric field. Nothing happens to E if you change T. But B is a current. So, for example, circling in this direction, that creates your B. You reverse time, the current starts circling in the other direction, so B flips sign. So that's why E dot B flips the sign, whereas E squared minus B squared doesn't flip sign under T. So both of these properties you can easily check, but T is a bit easier. So now we have here the standard term, which is CP even, and now we have a slightly odd term, odd in a double sense. It's also CP and T odd. Okay, and this term is often not shown, actually, if you look at a standard textbook of QCD. And there are two reasons. One good, one maybe not so good. The not so good reason is it's a total derivative. So you can check that this is a total derivative. Now, total derivatives are, let's say, tricky things. Usually, in the Lagrangian formalism, you simply discard them because they only contribute on the boundary. That would be a good reason to say, okay, we don't have it. It has no observable consequences. But this is not true for QCD, or probably not true. I should hesitate to add, because Carlos has written a couple of papers that says you can't observe it. But I'm now advocating at least the standard law. Okay, so I have to admit there's a crucial and slightly, still at the moment, I would say, open debate going on. But what I'm going to argue now is kind of the standard view as it has been presented for the last quite a few years. And the point is, gluon fields can have a topology. So you can have configurations of finite energy that have a non-vanishing contribution to the action and therefore to the path integral. And this supposedly makes this term observable. So let me add, but topological configurations that makes it observable. Now, it's observable, and so observable is a neutron electric dipole moment. Okay? How can you guess that this is a good observable? There are others, but this is experimentally a good one. Why? Gluon fields. If you look for gluon fields, look in a hadron. So this contains gluon fields. Because it's a hadron. It's a bound state of QCD. It has something intrinsically to do with the gluon fields. And you can convince yourself by the same argument of basically flipping essentially the time direction that an electric dipole moment violates T and Cp. And that's why this is a good observable. It's directly linked, and it has the same symmetry breaking property. So far, so good. Then you ask your favorite experimentalist, go ahead, vanish 20 years in the lab and produce a measurement. And what they tell you is, with a little bit of theory input from a non-trivial calculation, which again could be open to debate, but they tell you theta is less than 10 to the minus 10, because they have a ridiculously small limit on the electric dipole moment. And now you face one of those famous theory puzzles, being theta is a dimensionless number. The dimensions are exactly the same as this one. And, well, theta should be in a range of minus pi to pi, if you wish. Here you have some additional theory input. This is a bit too much for today, but essentially here is where the topology comes in, and you get some integer structure behind it. And the physical phases, and theta is a phase, are restricted to a range of minus pi to pi, because the redefinition of, so to speak, of the path integral to e to the I 2 pi doesn't matter. So, once you have such a range and such a measurement, this is when you become puzzled. Because at least in a, I would say, pretty theory, I would like to, throw dice for my parameters. And if I throw dice with this range, I get something of order 1. And this is most certainly not what is observed here. Okay, you could say Cp is a good symmetry, but Cp is broken in nature. The weak interactions already break Cp symmetry. And the weak interactions, you probably have all heard and kind of seen the weak Cp violation experiments to some degree. It always feels like it's a small breaking. But weak Cp violation is only small because it's weakly interacting. The actual angle that belongs to it is not small. The angle, the weak, or the CKM angle that is responsible for Cp violation is not small. It's roughly order 1. Okay, so in that sense, Cp is not a good symmetry. So this is small despite weak Cp violation. And this is a puzzle. And this puzzle is the so-called strong Cp problem. Okay. And by the way, here there are no clocks in this room. Okay, but I'm still hoping you'll wave me on when I'm way over time. Okay. Okay, that is the puzzle. Now comes the brief version of the amazing solution by Pache and Quinn. And the solution is very simple. You upgrade theta to, if you wish, theta plus A over Fa, where this is a field. And this is a constant. Okay? And let me call that A tilde, because now I'm going to do a trivial redefinition just for convenience. let me just call this combination over Fa. Okay? And so far you would say, okay, I've added a degree of freedom. I've even done something not so nice, because if I make this a dynamical bosonic field, so it's bosonic, then if you look at it, if I replace that, I put it here, I have a dimension 5 operator. I've even done something seemingly non-renormalizable. But let's not worry about that for the moment. The important thing is what happens now. Because if you now plot the effective potential as a function of A, or more precisely A over Fa, and I put pi here, I put minus pi here. And this is the effective potential in the sense of quantum field theory. That basically I'm looking at a homogeneous solution all over space-time. So I'm just exciting a constant, spatially and time-wise constant field. So I'm just adding a suitable current and ask how much energy it costs me. Okay, and I can insist, and this is in a sense what I do by assumption, the tree-level potential. The tree-level potential, I'm saying, is just constant. It doesn't matter which constant it is, but it's a constant. And why is that a good assumption? Well, because it has no preference for any value of theta. So this is completely agnostic about the initial value of theta, or of my A. So it says all A's are created equal. Okay, but now I can do QCD quantum corrections, and I find something amazing. So with QCD corrections, you get a potential that looks like this. And that, I claim, and Patrick Quinn did first, is a good solution to this problem. Because now, the minimum of my potential, and this is something you can show, well, again, with some caveats, but to otherwise an amazing level of non-perturbativeness, I would say, you can show from the path integral by an argument given by Witten. You can show that this is truly the minimum of the potential. The CP conserving value is the global minimum. But now you can see the solution at work. You start here with your field value, somewhere in the early universe. You don't care. But if you have a potential like this, what will happen is you go down. Systems tend to their energetic minimum. Okay? You just get a force, so to speak, for the field that drives it towards the minimum. Of course, you will now immediately argue, but of course you're cheating, because it will roll down and it will shoot up again, which it will do. But we'll see what is going to damp it. And this is indeed the next step after looking at the axion. But what will happen is essentially the oscillation that you would now get, you oscillate back and forth, is damped by the expansion. So the oscillations become smaller and smaller and smaller. And then at some point you're sufficiently close to this minimum. Okay? So, at this point, you have two things. You have, or you have actually more than two things. You have three things. You have dealt with your strong CP problem. So this gives you CP problem solved. The second bit is you have a dynamical degree of freedom. You have a new particle, because any dynamical field degree of freedom comes with a new particle. And this particle is the axion. 2 comments on the axion. Maybe also lessons for writing papers. This kind of trivial statement that you have a new particle as an excitation of this field that you introduced, and that it has certain properties, was unfortunately missed by Paget and Quinn. This is something that may come to haunt at least Helen Quinn when the thing is discovered. Because that could be the decisive thing about getting a Nobel Prize or not. So they missed this. Weinberg and Wilczek did some, what's in German called Abstauber. When you're directly in front of the goal line, someone kicks the ball to you, you do that. Okay? Not a huge effort, but you need to be there. That's the paper writing lesson. But this is, of course, also the thing that okay, and the other thing that you already have at this point, you will get some damping of these oscillations, but they are not gone yet. You have automatic energy density in these oscillations, and this gives you typically some form of dark matter. We will see how that comes about in a second, but this is what will be the dark matter in the case of axions and ALPs. It's just these remnant oscillations. There's nothing more to it. And this is really unavoidable. You have to start somewhere. If you start here, okay, would be possible, but then you have fine-tuned your initial condition to the same degree that you would have to fine-tune your initial parameter. So that would kind of, well, at least make the solution not really all that interesting anymore. So generically, you start with a value that is around 1, and you get some generic amount of dark matter. And we'll see how that basically also fits on observations of dark matter. Okay. Questions so far? Okay. Okay, then where is the eraser? So that's the quick and dirty basic story. And now one thing to take from that and keep in mind is essentially the axion action. And the axion action, now we need our bosonic field. So we have 1/2 d mu a squared. We always need a kinetic term. We can't do without. In principle, what we now have, at least if we are just looking at the kind of action after QCD effects, we could write minus V effective of this axion field. So we have an effective potential. It's exactly the one we have drawn here. For most practical purposes, it's usually just good enough to write the mass term. Why is that good? Because if you're interested just in these tiny regions around here, well, everything near its minimum is dominated by a harmonic oscillator, and that's just a massive particle. So there's not more to it. Indeed, it turns out that any self-interactions that are down here are really, really tiny. So they're in most, unless you go to something extreme, they're completely negligible for practical purposes. Okay, and then you have your minus 1/4, and let me write it like this. GA glue Axion G mu tilde. This is a defining interaction of your field. That's, so to speak, the must-have terms. But it turns out that in essentially any reasonable model, you also get terms like minus 1/4 GA gamma A F mu tilde, where this is the photon. And this comes about because whenever you have an interaction like this, you can check that the axion is, you can see it from here, the axion has to be CP odd. So the axion is a pseudoscalar. It's neutral. And therefore it has the same quantum numbers as the pion. And therefore it can mix with the pion. And if you crank the handle a little bit, you use this interaction, use a bit of QCD, you mix with the pion, and that usually automatically gives you an interaction like this, because the pion has an interaction like this. So it inherits a part of this interaction from the pion. You can also have some fundamental parts that basically arises when you say, oh, this is my higher dimensional operator, I would like to have a renormalizable theory, so I'm embedded into a more complete theory. And then you typically also get contributions to that, but it's essentially impossible to exactly cancel the contribution from the pion to the fundamental contribution. That would be some ridiculous tuning. So you typically have this interaction as well. Brief comment. If you look at this minus pi to pi, this tells you a little bit more about the nature of this particle, because in particular, if you look at the tree-level potential, minus pi to pi sounds pretty much like a circle. And which type of particles lives on the circle? Goldstone bosons. And, well, having no potential is one of the things of a Goldstone boson. That's why Goldstone bosons are massless. So this tells you, this thing here tells you it's Goldstone. And that's, of course, how it's fundamentally implemented. So it's because now, of course, you have a breaking of the symmetry due to QCD, it's a pseudo-Goldstone. And what it turns out now is that MA squared is something like, or MA, let me do it directly, MA, you can actually calculate the QCD corrections to some degree, and it's only QCD that breaks it, is something of the order of mass of the pion, decay constant of the pion, so the pions are here again, that's why it's QCD, divided by the scale FA, which already appeared here, which tells you the size of the interactions. So this is, let me just write it roughly speaking, this is alpha S divided by 4 pi FA. So you always get a coupling like that. And here you get alpha electromagnetic over 4 pi FA. But only proportional. There can be order 1 factors. Here this is much more fixed. Here you can have integer factors. So you have some integer factor here. But here you can have order 1 factors typically. Okay, but importantly, you have this ratio, and these things are known. And this is something like 0.6 milli-electron volts, 10 to the 10 GeV over Fa. So, what does this tell you? Very small mass, but non-vanishing. And the bigger you make your scale, the smaller your mass may be. Okay, yeah?
I'm sorry, I didn't get which symmetry is broken here, so you generate
Very, very good point. So I didn't specify it. So what you see here is only the Goldstone nature. Okay? So that you can guess from the structure. It's just a guess, if you wish. Then you can ask yourself, what is a suitable symmetry? And a suitable symmetry must have 2 things. It must be, at least at tree level, it should be an exact symmetry, because you want to have this tree-level relation, but only at tree level. And second, it should be anomalous, and in that sense explicitly broken by QCD effects, because, where is my term? Here, because you want to couple to your gluons in this way. And this coupling you have to generate. And this coupling doesn't look like a proper Goldstone coupling, because it has a GG dual. And Goldstones should only couple via derivatives. It secretly is kind of, because that's a total derivative, and that's where things get a bit iffy again. But at first, it doesn't look like it. It's indeed an anomaly. So what you want is a U1 symmetry, because that's what gives you the circle. And you want a U1 symmetry that is anomalous with gluons. And that's simply an axial symmetry. Axial symmetries, symmetries with gamma 5 involved, are anomalous. Quite generically, unless you have some accidental cancellation. And that's what you want. And that's what does the trick. So you want an axial symmetry with some particle that is coupled to gluons. And that's enough. Okay? And then Fa is the scale of spontaneous symmetry breaking. And from then, you just crank the handle. Of course, axial symmetry, that's why it's called the axion. And of course, also because Axion is a laundry detergent that at that time was, well, at least semi-popular in the US. You can even watch advertisements from the 60s or so, or 70s on YouTube. And you can still buy it, but I don't think in the US, actually, I'm not sure. Yeah, and also not in Europe, but I think in some other countries you can still buy Axion. Yeah, I saw someone. So that was, okay. Or did I miss someone? No. Okay, so that's the basic thing about Axion. So that's, the motivation is a strong CP problem, and that's typically the Lagrangian that you get. Why do I insist on the photon Lagrangian? Because that's the defining feature. Well, because that is the thing that you can most easily test. That is the thing that's experimentally accessible. People also try that one here, in particular actually here in Mainz. The group by Dima Butker looks for that coupling. Actually, I'm not going to talk much about this, so I can also tell it now. You can actually, combining this tiny little oscillation that we have left today with this coupling, you already know the predicted observable. The predicted observable is a neutron electric dipole moment that is oscillating a little bit. It's close to zero, it's really tiny, but it's oscillating. And that's something you can look for in precision experiments. Really precision experiments. It's a really tiny angle, yeah.
So this is something I never understood, the GA gamma-gamma coupling. You just argued that in some sense it is not a natural interaction for the axiom to have. It gets it through pion loops.
Yeah.
So in some sense, like GA gamma gamma should be highly suppressed because not only
No, it's not. It's a mixing. It's not a 5-loop effect. It's a direct mixing. So the mass of the pion and the mass of the axion, if you go into the natural interaction basis, are not diagonal to each other. So they mix. They mix with an angle that is essentially, well, QCD scale over FA. This is typically actually a small mixing. After all, this is a small angle. F pi is typically much smaller than FA. But that still gives you, well, you can easily calculate. The pion has such an interaction. That's a pion. And now you add a mixing with F pi over FA. That's the mixing angle that you typically get, because geometry-wise you can very naively think you have a scale F pi for the pion, you have a scale FA for the axion, but they are not entirely diagonal. Everything parameterized by F pi and FA. So the mixing angle is this one. And if you multiply that out, you get exactly this one, because this cancels. So you get typically 1 over FA. There is a coefficient that you can calculate. It's 1.92, plus minus some QCD uncertainty. Okay, so yeah, in that sense it's small because it's also suppressed by 1 over FA, but it's the same as here. Because anomalies are one-loop diagrams. And here you take the one-loop diagram for the pion and multiply it by the mixing angle. So in that sense, this is a kind of suppression that you get. But both of these interactions are tiny. In particular, if FA is large, really tiny interactions. Good news for our aim of dark matter, because, well, dark matter should not interact very strongly. Bad news if you want to detect it. Makes it harder. By the way, this is why people are certain that FA is fairly big. So Peche and Quinn still thought this is an electroweak scale. It would still be a small light particle, but not so light. But this is experimentally ruled out. So that's why people pushed up the scale. Yeah. To SU2, yes, you can also have that, and you typically get that. So in that sense, I should have written it, but this is the one that is essentially super hard to access. People have, in recent times, fiddled a little bit with Axion models where you violate this mass relation, and then this can become important, because then the limits get softer. But if you have a FA scale of 10 to the 10, you have no chance, at least not to my knowledge, that I have any idea how to test that. The limits for weak interactions are, let's say, would be for FA of the order of 10 to the 3. So I would say in any reasonable model, it's there, but it's super hard to test. Even harder than all the others. Okay? Good. That's the axion. And that also brings us to an axion-like particle. And that is actually a nearly trivial statement. It's an axion without this relation. And of course, not solving strong CP. Okay, so it's just a wild generalization. Okay, so you simply say, okay, I have a pseudo-Goldstone boson. It's a pseudo-Goldstone boson, it's a pseudoscalar, it's neutral. It comes from some spontaneous symmetry breaking, so I'll typically get a relation like this for gluons and photon couplings, and that's what interests me. Okay, so it's really literally giving up this mass restrictions, which in turn, of course, gives up solving the strong CP problem in most cases. People have worked and made some, let's say, non-trivial Axion models where you can still solve the strong CP problem and violate the mass relation. But this is, let's say, challenging model building. For practical purposes, you can just take any pseudo-Goldstone boson, couplings like this, any mass relations that you like. And the point is simply, if you plot mass against coupling and plot your limits, you don't have a line, you have areas for experimenters to target. Yeah? So you can, this is where model building comes in. That's where you can become creative. You could have any anomalies that you like. Okay, so you just need an anomalous symmetry that gives you a mass. Good thing about anomalies are that they typically exponentially dependent on the coupling. After all, this is secretly exponentially dependent on the QCD coupling. It's a QCD scale, lambda QCD, which is e to the minus 8 pi over g squared. So in that sense, it can be very small. So you have sensitivity to the coupling at the UV scale. So that's one generic mechanism. You have an anomaly. And this is, I would say, also what you typically find in theories like string theory, where you have plenty of, well, actually string theorists don't call them ALPs, they just call them axions. And then they stress it's a QCD axion or not, okay? But there are plenty of them. You have plenty of pseudo-scalar fields which come together with a moduli. So the kind of shape and size determining fields for your extra dimensions. And they have couplings like this, they have structures like this. And yeah, string theorists call them axions. They are often, not always, anomalous and have therefore a small mass. You could also say, let me take any Goldstone boson and say, oh, but quantum gravity never preserves any symmetries, so I should just add some mass. True, but I'm not sure if I entirely buy that, because this mass can be really, really tiny and might not be phenomenologically interesting, because gravitational effects could be incredibly suppressed for anything that you can access. But there are papers in both directions. Let me put it like this. Okay, more questions? Okay, then that's the basic for the axiom. Let's make it dark matter. Let me just, where's my metric? Did I lose a page? Just 1 second. Well, I'll have to make it up. Don't bet on any prefactors in any case. So, I should have written a little bit more. Okay, so dark matter and its production. Okay, so now we want to talk about the production of this dark matter. The basic idea is already here. So what do we need? Well, we need the equation of motion. Of an axion in, well, preferably an expanding universe. Or more precisely, a Friedman-Robertson-Walker universe. And I guess you've heard about that already in the dark matter lecture. But just to specify it, but this is a page I lost. Anyway, I'm optimistic that I can manage. Let me just specify the metric as dt squared minus a of t squared dx squared. Okay, where this is the so-called scale factor. Now, this specifies the expansion. So, what is the equation of motion? The easy way to write it down, but not to calculate, is now to write, well, if I do that, ignore all the interactions, and interactions are small, so I don't count them. I just look at my scalar field. Well, it's a Klein-Gordon equation. What else can it be? This is a Klein-Gordon equation. And now the question is just what's in the box. In flat space, it's d mu d mu. That's easy. And I'm not going to do it in all generality, but let's consider spatially the constant solutions. So they are just functions of time. And then what we get is this is a dot dot plus 3h, which is a dot over a dot plus m squared a equals 0. Okay? Yeah, it's an amusingly simple equation. It's an equation you probably have seen a long, long time ago in probably first year physics. It's a harmonic oscillator with a little bit of damping. And the damping is given by h. Just out of curiosity, this is of course something you want to calculate. You want to go from here to here. And the non-trivial bit is this damping bit here. And indeed, you want to understand the 3. Why is it 3 times h? And I think, well, you can simply do it, crank the handle. You can calculate your box as a combination of covariant derivatives in GR and calculate many Christoffel symbols and arrive at the result. But just as a cute little trick, and you can maybe fill in the details as an exercise, my claim is, the easy way to see now I understand the joke, which was my stupidity. I have a double meaning for A. It's a scale factor and it's the axion field. Okay. Axion field, axion field, axion field, scale factors. Very good, yeah. In my notes I have 5, which solves the problem, but I somehow started with A's. Where do you see this easy now? The trick is here. You now need minus the square root of g, 1/2 d mu a squared. Or let me actually be explicit. Let me write this one. Minus m squared a over 2 a squared. And that's the complicated version, because now I have a GR covariant derivative here. That looks hard, but it's actually not, because square root of minus g, and this is 1/2 d mu a squared minus m squared over 2 a squared. And the reason is simply the covariant derivative on a scalar or pseudoscalar is simply the ordinary derivative. So no covariant derivative needed. And once you write it like this, and this is the exercise that's not, that has not been sent around by me, once you write it like this, you can do your functional derivative with respect to A to obtain the equation of motion. And you don't have to worry about covariant derivatives anymore. You just need to know what minus square root of g is. That's the only thing that appears here. And of course the metric that is secretly in here still. But this is still a fairly trivial part if you go for these. And that thing is easy, because after all, this is specifying you the metric. The metric is now 1 a squared, a squared, a squared. And of course we need a square root and a minus sign. The determinant is easy to see. It's minus a to the 6. With a minus sign, it's a to the 6. With the square root, it's a cubed. And now you see where it's coming from. There is a time derivative of a cubed somewhere in this equation of motion. Of course, when you do the partial integration. Okay, but try it. This is, I think, a relatively straightforward way to get that without doing any Christoffel symbols. Okay, and now we are basically done with our Axion equation of motion and our dark matter production, because now we have to solve this challenging equation. And this challenging equation is called a damped harmonic oscillator. And I need a new piece of chalk. And this is a harmonic oscillator. And now we have interesting regimes. This is something that you probably remember from first year physics. The first regime is, and the order is by time in cosmology, not of importance if you wish. If I have a damped harmonic oscillator, h is my damping constant, or 3h. If I have that, and I put an enormous h, I make it the damping constant really, really big, much bigger than the mass. That is first case. That's overdamped case. And in this overdamped limit, well, any remembering what's going on in the overdamped limit? What's happening to your oscillator? Is it happily oscillating? No, I hear it. It's just stuck. Huh? It's essentially stuck. Slow evolution. Because essentially, what you have is something like A of t, and I'm really taking this to the extreme now. You get A of t is some integration constant A1 plus A2, another integration constant, e to the minus 3ht. This being huge, you don't need to wait long. It's gone. Okay? So you're essentially stuck. So no movement at all. So the field is stuck. There is some ultra slow movement on a time scale that is suppressed by h. Okay, it's something like ma squared over h, but it's suppressed. And that is essentially what you have during the early phases of the universe. That's inflation, for example, at least if you have sufficiently high scale inflation. And sufficiently high scale really just means that, and that's not a strong condition if you remember your mass relation. Okay? So that's the early universe. Nothing happens. Field is pinned down. And then you have the opposite limit, is the weakly damped. And again, you can do a relatively quick calculation, and you get essentially A of t is some integration constant, let me call it A0, e to the minus I omega t plus, if you wish, some phase delta. You could also choose A0 to be complex. And then you have an e to the minus 3/2 ht, where I've assumed h is roughly constant. If you don't assume that, you do a t integral of h. Now, what do you have here? Of course, plus Hermitian conjugate. What you have here is simply an oscillation with frequency omega. And what is omega? Well, omega is ma. So you have an oscillation with the frequency equal to the mass and an amplitude that is suppressed by the Hubble scale, or an exponential of the Hubble scale. Okay? Now, this bit, if you now look at it and you can express it as a function of the scale factor, it's an integral of h of t, h being now the scale factor over itself, or the scale factor derivative over itself. What this is nothing but proportional. The scale factor choice. But if you integrate its scale factor, this was really stupid. This is now the scale factor. It's the scale factor to the power minus 3/2. Okay? And this is, of course, if you now think in terms of an expanding volume, is the volume that you expanded to the power minus 1/2. So the amplitude scales like the square root of the volume. That sounds a priori a little bit weird. What does the square root of the volume tell me? Well, let's ask not about the amplitude of the field, but let's ask about a physical quantity. And a physical quantity, is energy density. This is something you can measure, the energy density in your field. And the energy density in our axions, what is it? Well, it's 1/2. It has potential energy, so mass turbo. It's, after all, essentially a harmonic oscillator. 1/2 m squared a squared. Gives you the potential energy plus the kinetic energy, 1/2 a dot squared. That's what you can get from the energy momentum tensor, if you wish. These are just the energy density components, so the 0, component of the energy momentum tensor. And now you look at it in the weakly damped regime. It's pretty easy. You have your scale factor squared, or your amplitude squared, and you can also write it, and let's maybe use that one, it's perhaps even easier. It's A0, if I just go from complex to real fields, times cosine MA times T times e to the minus 3/2 HT. If you just take the complex phases and take the real part. Okay, if we have that, I have 1/2 MA squared, big bracket, A0 squared, sine squared, then I'll add something here for the kinetic term, but let me already add the volume factor. It's e to the minus, because we need to square it. It's always the square. It's e to the minus 3ht. And now let's do the kinetic part. It's 1/2. Now, I have two t-dependent things, so I would think I need to do the product rule. But there's one thing that is fast, that's the oscillation, and one thing that is slow, that's the decrease in amplitude. So if I just go for the leading order terms, A dot is simply MA. Oh, this should have been cosine, sorry. I took a cosine plus delta. And squared, sorry about that. But if I do that now here, I get MA squared, because I take A dot squared, I take the derivative, sine squared, argument, and A0 squared. So if I combine all that, I get 1/2 plus order H over MA terms. So these terms are suppressed if the Hubble scale is smaller than the mass. So I get 1/2 MA squared, cosine squared plus sine squared, it's 1. A0 squared, that looks already much simpler. That's the whole top bracket. And this one is now not the square root of the volume. It's e to the minus 3 and not 3/2. It's the volume. So that is, in a sense, the volume at T0 divided by the volume at some later time. Okay? So I just need to have the ratio of the volumes. And this is now something very physical. I expand my space, and my energy density goes down like 1 over the volume. This is something that you've probably already seen, also I guess in the lecture earlier this week. If something goes down like 1 over the volume, this is exactly what you want for dark matter. So it has the right volume dependence for dark matter. And the reason is simply, just imagine particles at rest being sprinkled around your space. The particles are conserved. You expand, and their density goes down like 1 over the volume. And that's what you expect for a non-relativistic cold gas. So this is exactly what is expected for non-relativistic cold gas. Okay? So this is really the essential bit. It's really like 1 over the volume. And that's what already tells you. It behaves like non-relativistic or even non-moving particles, if you wish. Okay? And that's what you want for dark matter. This is simply a case of if it walks like a duck, quacks like a duck, it's probably a duck. So in that sense, it's dark matter. Okay? This is the only thing that you need. Okay, how am I doing for time? Oh, probably a couple more minutes. Okay. 13, okay. Good. But let's then nevertheless understand a few of the features of this behavior. This is already the kind of crucial bit. But how can we really understand that this is non-relativistic dark matter? As I said, the volume scaling tells it all to a large degree. But you could also look at it from the perspective, and let me just wipe a little. Let's take the cosmologist, or dare I say the astronomer cosmologist point of view. Because astronomers often do not really care about particles. They have fluids. Let's take the astro point of view. If you look at a more astro-oriented book on cosmology, you will find a treatment of dark matter as a fluid. And what they specify is an ideal fluid which has a T mu nu, an energy momentum tensor, that is something like rho p p p. So it's isotropic, it has a density, it has a pressure. That's what characterizes a fluid. And they're going to tell you that the equation of state in a proper simple world is given that the pressure is linearly related to the density. This is called W in most papers or books that you look at it. And this is the equation of state parameter. And observation the equation of state parameter for dark matter is equal to 0. So it's pressureless. This actually makes a lot of sense, because if you look at this, this is measured the pressure in relativistic units. So the pressure in terms of the total mass energy. And if you think of a non-relativistic gas, of course in undergrad physics you get some ideal gas relation that the pressure is proportional to the temperature or whatever. But the pressure is proportional to the velocity squared. That's, if you look at the microscopic picture, it's the number of, in a sense, bumps into your wall, which is proportional to the velocity, times the momentum transfer, which is again the velocity. So it's velocity squared. And non-relativistic velocity squared is simply close to 0. That's all. So this is essentially v squared in the non-relativistic. And that's approximately 0. It's 10 to the minus 6 or whatever you want to have. It's really small. And that's why dark matter has no pressure. That's the idea of a non-relative fluid. Okay. Just as a comment, of course, this is why they like it. Photons can also be described in that way. It's just an equation of state parameter equals 1/3. So that's a relativistic gas. Dark energy, the cosmological constant is -1. That's more weird, but still you can press it into this way. Okay? So now let's take our, let's say, particle physics point of view, or our Lagrangian point of view, and then we can actually calculate T mu. This is not really difficult. You just take your action. Oh, I erased the action. I'm pointing at the wrong thing. But you take your action and you take the derivative with respect to the metric, and then you have your T mu nu. That's the easiest way to get T mu nu. So if you do that, you get a pressure and a density. You get rho, that we already had, 1/2 a dot squared plus 1/2 m squared a squared, and you get a pressure that is 1/2 a dot squared minus 1/2 m squared a squared. And we have already seen that's pretty much constant times, let's say, a factor like this. So this is sizable. There's no cancellation. Indeed, both of the terms add up. If you now look at the pressure, there is not much more happening here. It's just that you get your 1/2 ma squared, a0 squared, 0, V of t, just factoring out all these factors. But now you have the A dot term, which is sine squared, but you have minus the potential energy. This is minus. And now, well, the constant is actually the same. So this pressure is actually not 0. But it does something funny. It oscillates wildly. Okay? And it oscillates very, very quick. Indeed, it oscillates on a time scale. So this bit oscillates. With frequency, MA. And MA is much, much bigger than the Hubble scale. So this oscillates really quick. So in one bit of universe expansion, you have many, many oscillations. So the smart thing to do is, let's look at the average over many oscillations. Well, average over many oscillations is 0. Because sine squared and cosine squared averaged, both of them is a half. Which is 1/2 minus 1/2. If you do the averaging, that's why you have 0. So you don't really have 0 pressure, but an average. And that's what counts. If you really are interested in the long term of evolution, you really have 0 to an amazing degree because you are averaging really, really quickly. That said, this gives some funny behavior if you're in the kind of boundary region. When H is order MA and you somehow have a significant part of the energy density in that, then you get some funny behavior. But whenever it counts, in the really late universe, when all these approximations are valid, your pressure is indeed 0. Okay, so that's the astronomer's point of view. And let's come to the final point of view. And the quantum mechanical point of view. You can also look at it from the point of view of quantum mechanics. And this is perhaps the simplest, because it tells you something about the particles. So what is velocity in quantum mechanics? Well, just as in mechanics, I would say it's momentum divided by the mass. Now, what is the momentum operator? Well, it's a spatial derivative on your field divided by the mass. And, of course, this is, again, my Axion field, as usual. Okay, so this is the Axion field. It's a spatial derivative, and now what we calculated was spatially constant field. It's 0 if it's spatially constant. Okay. Did you catch me cheating? Where did I cheat? Exactly. I assumed it's spatially constant, so I put it in already. So, but, and this is where it, well, we'll see if my drawing skills are up to the task, but let me do a one-dimensional world before inflation. 1D world. This is space. This is my Axion field value. And I'm very early times, before inflation. Okay? Let me slightly change that. Oh. Let me do it like this. I just didn't want to have a maximum. It doesn't matter, it could also be a maximum, but for the point I want to make it, it's not necessary. So we are here, or we are going to be here. Okay, we are in x equals 0. And this is before inflation. But now we are expanding. And we are expanding a little bit. And I've expanded a little bit. I've now expanded roughly this region here. Oh, I should have ended a little bit earlier, so let's go it down a little bit deeper. So I've expanded this region here. Stretched space, so the field values are now going here, from this point, to this point, which is here. And everything else is far away. So I've expanded a little bit, but let me do it again. I now take this one, and roughly the same, and I expand it again, and it's now going to be even flatter. So if I expand, and I always look at the same size spatial region, I'm zooming in on a smaller and smaller region originally. And that's why it gets flatter and flatter and flatter. And this is the whole point of inflation. You're taking a tiny little region here, and you blow it up to the size of the complete observable universe. That's what inflation does for you. Really tiny region, and you blow it up to the observable universe. And then you automatically have the same field value everywhere, or more or less the same field value, in all of the observable universe. So in all observable universe today. And that's a fairly constant field. Indeed, you can make some estimate. Let me just, because I'm also, I think, by now over time, let me now make some estimate for that. Well, this thing should change at most order 1 over all of the observable universe. Well, the observable universe, the size of the observable universe, is of the order of the Hubble scale. So this thing is going to be Hubble today divided by the mass of your axion, and whatever value you take, this is a ridiculously small velocity. So you can put in some numbers, but if you do something like that, let's say if you get something like 10 to the minus 25, so even accounting for the speed of light, that's slow. I think times 3. Meter per second, so that's accounting for the speed of light already, so 3 times 10 to the minus 25 meters per second for a mass of 1 electron volt. You can make the mass a little bit smaller, let's say 10 to the minus 10, it's still small. It's a nuclear radius per second. And just imagine ordinary dark matter velocities in our environment are about 300 kilometers per second. Totally negligible. So this is, I would even venture to say, this is about as slow as you can reasonably get with anything. So this is, in that sense, the coldest dark matter productions that you can achieve. The only input is you do your inflation first. That's admittedly only one of the possibilities for QCD axions, but the one I would like to focus on here. It simply assumes that the axion exists before inflation or the axion-like particle. And then all that follows automatically. You get these super cold, essentially at rest produced particles. And then only gravity can speed them up again. But the production is colder than any WIMP, even if you go super light. Okay, I think I've exhausted my time. And yeah, maybe questions or, yeah? Thanks.
So maybe this is a naive question. If you are performing like an and you blow a very little piece up to the size of the observable universe, does it matter that it's spatially constant? Because
Originally it doesn't. That's why I was thinking. So originally you can have any wild configurations. That's what you typically will have. And then it only matters where you sit today, because this tells you which of these regions you will see. If you're sitting here, you will see this field value. If you're sitting here, you will see a different field value. So what this tells you, in a sense, is depending in which causally disconnected patch today you are, you will have different initial field values. It basically gives you a mechanism to have a random selection of field values for your initial values. So in that sense, this is a good thing and a bad thing, because, well, you could pick, depending on your Axion or ALP parameters, the one that fits your density if possible, and we'll calculate the density tomorrow. But you could also say it's a bug, because you're not really predicting the initial value. You're just saying, okay, I take some generic initial value, and it seems to fit with what I observe. And I can always adjust when I know the mass or something like that. But the point is, it's really random in that sense. Okay. Yeah?
And then also about the inflationary argument, does this mean that the patching instantly has to be broken during inflation or before inflation?
It has to be broken at least during a substantial part of inflation. Depending how strict you want to make the argument, during the last 60 or so e-volts that count. 60 is, by the way, I should make this remark because I always stumble upon it. Some people have their mind set to 60, but the 60 only holds for relatively high inflation scales. For if you have a low scale inflation model, it can be easily as small as 40 or so. This is just a comment. But yes, so it's assumed that it holds during this last 60 or 40 or something e-volts that are relevant, that we are kind of setting as a minimum condition for inflation. Generically, this is actually not the challenge, because usually you imagine your spontaneous symmetry breaking mechanism to go something like this. you have your Mexican head potential at 0 temperature. So T0, it looks something like this. T larger than the scale of symmetry breaking. And indeed, during inflation, this is actually something intrinsic to inflation, the universe is fairly cold because everything that's radiation will be expanded away. So the temperature drops dramatically, like 1/8. So it's e to the minus 60. Okay? So you will generically be in this situation during inflation. The only trick is, after inflation comes reheating. And now the question is your temperature after inflation big enough to do that? Because then, what happens now is you go back to this, then you cool down, and then you're sitting here, and then you're going randomly any direction depending on your causally disconnected region. That can happen, doesn't have to. Could be just that the reheating temperature never reaches that, and that's what you have here. But if this does happen, that thing is called pre-inflationary scenario. That would be post-inflationary scenario, because you are kind of creating the axion for the last time. It always counts what you do last time. So the last creation of the axion is after inflation. That's why it's post-inflationary. So then you have this random things going on here. And now you might vary. Okay, huge density here, tiny density here, enormous fluctuations. You're absolutely right, you will get those. Now comes the funny part. You can calculate the size of the relevant regions, because the relevant regions are the causal regions when the axion acquires its mass, and that happens during the QCD phase transition. So this is a fairly fixed size scale. So basically, within a horizon, you homogenize until you get a mass. So now you have horizon at QCD scale, and you can ask, how big is that today? And it's not huge. This is a surprising thing. It's, say, solar system sized. So you have these patches which are solar system sized. Perhaps a bit larger, it depends a little bit on the parameters, but it's small on cosmological scales. And now comes the funny thing. So in that scenario, you really have order 1 density here, possibly even much bigger than order 1. Small density here, and all these kind of random patches. But they're all small. And the funny thing is we don't know anything about dark matter on these scales. We have very good global information. We have galaxy-sized information. But solar system size, no information at all. So what you get is essentially the average. And at that point, you're actually in a better business, because the average is super predictive. You get one average. It's assuming this average to a perfect degree, because you have many, many, many patches. So you have your prediction. So the post-inflationary scenario puts you basically a dot in parameter space where you get the right density. So far, so good. You could start celebrating and measuring exactly at this point. Only trouble is, there's again a topological issue, because if you look at neighboring disconnected pieces, it could be such that effectively you're going around the circle once. And that's a stable configuration. It gives you a string, a cosmic string of axions. And, well, bottom line is, people have tried to calculate how much these axion strings contribute to the density, and it's uncertain by at least a factor of 10. It's super difficult to calculate, because you need to solve the equations of motion for a classical field. So far sounds easy, but you need resolution of the thickness of the string, and you need a volume that is, because you want to see the whole string through the universe, that is, again, the size of the universe at QCD scale. And, well, the thickness is 1 over the Paget-Quinn scale, so it's really, really thin. The size of the universe is not huge, but much, much bigger. So you have, again, you have to have resolution of the order of Paget-Quinn scale, volume of order this Hubble scale at QCD, and that's, I think, about e to the 60, again, in ratio. And that's a lot of lattice points. So if you want to do a lattice calculation, your computing runs out of steam. So people can do some hierarchy, but it's not converging. They don't know where it ends if you extrapolate to 60. And they differ by orders of magnitude. So this unfortunately destroys the prediction, but this is of course a worthy task. So if you like calculating things precisely, do a proper calculation of Axion string production. If you do that, you get Z number for the Axion mass that would give you dark matter in this scenario. And then someone could measure and find it there. That would make you famous. So that's an incentive. That is the second possibility. But in that sense, there's a similar range of uncertainty as in the first scenario. It's just a slightly complicated mechanism. But the features are similar. The observable features, you would say, oh, but I would see this thing with the huge fluctuations. Not really. We simply do not know. They could. A generic prediction is actually that you get these tiny clumps because at some point these overdense regions collapse under gravity. People have some hope to see these, for example, whatever gravitational lensing, but it's not easy. They are fluffy. They are not black hole-like typically. Very hard to see objects. But it's also not excluded because on all scales that you can see, you average. Okay.
Any more questions?
Yeah.
So maybe the Axion corresponds to the axis symmetry,
Yeah.
but is there also then a particle corresponding to the radial symmetry?
So axial in this sense means, I should maybe have been more precise. So axial symmetry refers to the fermions because you get anomalies with fermions. Okay? So anomalies are always connected to fermions. And what it means to be axial is that your left-handed fermions transform under the symmetry like e to the, let's say, minus alpha psi left. And your right-handed fermions so they are going in the opposite direction. That's what axial means. It's not about the scalar potential. It's about the transformation properties of the fermions. And such a symmetry is typically anomalous. You can also write it, and that's perhaps also a common way to see it. I should put i's here. I forgot the i's. Depends now on your choice, minus I alpha gamma 5 psi, if you take a Dirac notation. So it's always those involving a gamma 5. That's what axial means. It means you make a distinction between left and right-handed fermions. Yeah.